Okay, let's talk about interpretations of the derivative. We've started talking about where the derivative comes from and what it means. And again, the derivative is the slope of the tangent line. We saw a couple lectures ago that we can get that tangent line by taking the secant line and getting closer and closer to the spot we want. So when we talk about the derivative, we also need to look at its units. And the best way to sort of see what's going on with that is to remember where the derivative came from. Okay? So we often notate the derivative with the prime symbol. Okay? But thinking back to that secant line, we were doing change in y over change in x to get the slope. The slope of the tangent line is the derivative. So this derivative is actually the change in y over the change in x at one point. Okay? There's a famous mathematician, his name was Leibniz, and he went on to then come up with another notation, okay, that represented the taking of the derivative. Okay, dy dx. And again, that's just represented by the change in y over change in x. This is called delta in Greek, so that hence the d. Okay, so this is alternate notation, meaning take the derivative. Okay, why is this important? Writing it this way is going to help us sort of understand where the units come from. Okay, so the units of a derivative. Okay, so the units are going to be the units of the dependent variable, okay, which is usually y, but will be other things that we'll look at, over the units of the independent variable. So if we can figure out the units of each of these, we can then find out the units of the derivative. Okay? The units will be given to you in context in the problem that you're working on. So you'll be able to look at an example, see which one is a dependent and independent, and then figure out the units of the derivative accordingly. Okay? So let's say we have an example like this. The cost in dollars, C, representing the cost, okay, is given based on the length of a fence in meters M. Okay, so I'm telling you the variables here, which can be written as C equals F of M. Okay? There's usually a sentence at the beginning of every situation where it's going to give you the setup of the problem, tell you the variables involved and what they're based on. So what this says is the cost of some project, okay, is a function of the number of meters of fence you're putting in. Okay, so say you're building a fence on your farm, you want to know the total cost, it's going to depend on how many meters of fence you have. Well, if we want to talk about the derivative of this function, okay, f prime of m, okay, we can talk about the units by doing the units of the dependent variable over the units of the independent variable. Okay, again, the dependent variable takes the place of y. It's something equals a function of something else. So here, our dependent variable is C cost. Well, what are the units of the cost? That's going to be dollars. Over the units of the independent variable. That's the number you're plugging into, the number that's changing, okay, function of m, which was meters. So meters here is our independent variable. So here, okay, our derivative then has units dollars per meter, okay? We'll be using this a lot now that we sort of know how to calculate it, and you'll get used to figuring these things out, but this is just the basics of why it is the way it is, okay? Units of the dependent over units of the independent. Okay, we'll look a lot more at these after the video and do some examples based on this. Okay, so again, that's units. Something else that we can do with our newfound knowledge of derivatives. Is use the derivative to estimate things about the function that we don't know. Okay? And this is a process that is called local linear approximation. Now, what local linear approximation does is it says, okay, we know information about this function at a point. We also know information about the derivative at this point. So we can use that to construct the rest of the function. Okay, so that's really handy if you only know about the function at a point to find out about the entire thing. What does that mean? Well, the basic formula, okay, looks like this. F of new equals f of old plus f prime of old times new minus old. Okay, let's talk about what these words mean. New is going to represent the number that you are trying to approximate. Okay, you're going to be estimating the value of a function at a point. That's this new number. F of old and f prime of old, that's going to be the information that's given to you, that you already know, that you're using to get this new information. Okay, so what does this look like? Well, let's say I tell you that f of 15 equals 300 and that f prime of 15 equals 30. Okay, so now I've given you information about the function at a point. We don't know if it's a parabola or a line or what. We just know that when you plug in the x value of 15, the y value is 300. Okay? The other piece of information that I've given you is that the derivative, or the rate of change at that point, is 30. Okay? If and only if you have information about both the function and the derivative, can you use local linear approximation? Well, we do. We have information about the function and about the derivative. So now I can ask you things like, estimate f of 30. Okay? So now I want to guess what's going on with the function, okay, when x equals 30. What will the y value be? Well, I don't know. Okay? The truth of the matter is this is just an approximation, which means it's not an exact science. It could be way off, but this is our best guess based on what we have. So the formula says now the one I want, the new information I want, is 30. So my new number is 30. Old is the number that I have information about, which is what's going on at 15. So f of 30 will equal f of old, which is f of 15, plus f prime of old. Again, old is 15 because that's the point, the x value I have information about, times new number, which is 30, minus old number, which is 15. So what I'm saying here, before I plug in all the numbers, is that the y value at 30 is going to be the same as the y value at 15 plus some increment, either added or subtracted, depending on if this is positive or negative, based on the rate at which the function was changing at that time. So when we plug in the corresponding numbers, f of 15 was 300, okay? F prime of 15 is 30, okay? 30 minus 15 is 15. So 300 plus 30 times 15 equals 750. So that is my best guess, based on the information I have, about the y value when x is 30. Okay, so that's how I plug things in. Now I need to point out that it's very important at the end of this equation that you do new minus old.